Hello, everyone. Today, we're diving into a fascinating branch of mechanics called kinematics of particles. Now, don't let the technical name intimidate you. At its core, this is all about understanding how objects move. Let's break down what kinematics really means. In the world of mechanics, kinematics is like the storyteller of motion. It describes how objects move without getting into the why. We're not concerned with forces right now, just the pure, beautiful mechanics of movement. For particles, this means we'll be exploring some key concepts: position, velocity, acceleration, and trajectory. Imagine you're tracking a ball's journey, where it starts, how fast it's going, how quickly it's speeding up or slowing down, and the path it takes. That's kinematics in action. Let's start with the simplest type of motion, rectilinear motion. This is just a fancy term for motion in a straight line. Picture a car driving down a perfectly straight highway or an elevator moving up and down. We'll look at three crucial parameters here: position, which tells us where the object is; velocity, which shows how fast it's moving; and acceleration, which reveals how quickly its speed is changing. It's like tracking a point moving along a single line. Simple, yet fundamental to understanding more complex motions. Now, let's zoom in on these key parameters. Position, represented as xt, is like the object's address on our straight-line path. It changes with time, telling us exactly where a particle is. Velocity, v(t), is the rate of change of position, how quickly that address is changing. And acceleration, at, is the rate of change of velocity, how quickly the speed itself is changing. Think of it like this: position is where you are, velocity is how fast you're moving, and acceleration is how quickly you're speeding up or slowing down. Here's a special case: uniform rectilinear motion. This happens when velocity is constant, meaning no acceleration. Imagine a car cruising on cruise control, maintaining exactly the same speed. Our equation here is simple but powerful: x equals x plus vt. Let me break that down. X is your current position, x is where you started, v is your constant velocity, and t is the time that's passed. It's like saying where you are now equals where you began plus how fast you're going multiplied by how long you've been going. Now we're getting more interesting. Uniformly accelerated motion is when acceleration remains constant. Think of a car smoothly speeding up or a ball falling under gravity. The key here is that the velocity changes at a constant rate. This is where physics gets exciting. We can predict exactly how an object will move under steady acceleration. Whether it's an object falling, a car accelerating, or a rocket launching, this principle helps us understand and predict motion with remarkable precision. Not all motion is as predictable as uniform acceleration. Non-uniform acceleration is when the rate of change of velocity isn't constant. Imagine a car in city traffic, sometimes speeding up quickly, sometimes braking hard, sometimes changing speed unpredictably. This type of motion is more complex, requiring more advanced mathematical techniques to analyze. It's where kinematics becomes a true detective work, tracking changes that aren't as straightforward as our previous examples. Let's step up our motion game. Plane curvilinear motion is motion along a curved path in a two-dimensional plane. Think of a roller coaster, a ball's arc in the air, or a planet orbiting the sun. Unlike our straight-line motion, here we need vector components to describe the movement. We're not just looking at how fast something moves, but how its path curves and changes. This is where motion becomes truly fascinating, no longer constrained to a simple line, but dancing across a plane. This slide explains the vector representation of a particle's motion. It includes the position vector, denoted as r of t, which is the particle's position at time t. The position vector is expressed as the sum of x of t times the unit vector I and y of t times the unit vector j. The velocity vector, denoted as v of t, is the derivative of the position vector with respect to time. It is expressed as the sum of the time derivative of x of t times the unit vector I and the time derivative of y of t times the unit vector j. The magnitude of the velocity vector is the square root of the sum of the squares of the time derivatives of x of t and y of t. This represents the speed of the particle at time t. This slide explains the vector representation of a particle's acceleration. The acceleration vector, denoted as of t, is the rate of change of the velocity vector with respect to time. Mathematically, it is expressed as the sum of the second derivative of x of t with respect to time times the unit vector I and the second derivative of y of t with respect to time times the unit vector j. The magnitude of the acceleration vector is the square root of the sum of the squares of the second derivatives of x of t and y of t. This represents the total acceleration of the particle at time t. Breaking down motion into components is like being a motion detective. We're separating complex movement into simpler, manageable pieces. In a curved path, we can resolve motion into horizontal and vertical components, or tangential and normal directions. It's similar to how a complicated dance move can be broken down into simpler steps. By understanding these individual components, we can predict and analyze even the most complex motions with remarkable accuracy. Let's now see the path equation. When the trajectory of a particle is known as y equals f of x, we can derive the velocity and acceleration components. The slope of the tangent to the path is represented by dy over dx, which gives us the instantaneous rate of change of y with respect to x. The velocity components are v sub x, which equals dx over dt, and v sub y, which equals dy over dt. These components describe the particle's motion along the x and y axes. The acceleration components are the sub x, which equals the second derivative of x with respect to time, and a sub y, which equals the second derivative of y with respect to time. These components indicate how the particle's velocity changes over time along the x and y axes. Projectile motion is where physics gets truly exciting. Imagine a cannonball launched into the air or a basketball arcing towards the hoop. This is a perfect example of curvilinear motion under uniform gravity. What makes it magical is how we can predict exactly where an object will land by breaking its motion into horizontal and vertical components. The horizontal motion remains constant, while the vertical motion is influenced by gravity. Engineers use these principles in everything from sports science to ballistic missile trajectories. Next time you throw a ball, you're actually performing a complex physics experiment without even realizing it. In special cases of curvilinear motion, such as circular motion, the particle moves along a circular path with a specific radius, denoted as r. The tangential velocity of the particle is given by the product of the radius and the angular velocity, expressed as v equals r times omega, where omega is the angular velocity. For acceleration, there are two components to consider. Centripetal acceleration, which keeps the particle moving in a circular path, is given by a sub c equals v squared divided by r. If tangential acceleration exists, the total acceleration is the square root of the sum of the squares of the tangential acceleration and the centripetal acceleration, expressed as a equals the square root of a sub t squared plus a sub c squared. The study of kinematics of particles is crucial in various engineering applications. For rectilinear motion, it is essential in the design of conveyor belts, elevators, and robotic arms. Understanding curvilinear motion helps in analyzing projectile paths in ballistics and designing trajectories in sports like cricket or basketball. Circular motion principles are applied in the functioning of centrifugal pumps and turbines, ensuring efficient operation in many mechanical systems. Welcome to the coordinate system that makes motion tracking possible. Rectangular coordinates use fixed x and y axes to describe a particle's position, velocity, and acceleration. Think of it like a map, where every point has a precise address. The x-axis represents horizontal movement, while the y-axis shows vertical motion. This system is incredibly versatile, whether you're tracking a robot's movement, analyzing a projectile's path, or studying complex mechanical systems. By resolving motion along these fixed axes, we transform abstract movement into something we can mathematically predict and understand. The position vector is like a GPS coordinate for our particle. It tells us exactly where an object is in space by specifying its x and y coordinates. Imagine placing a pin on a map. That's exactly what a position vector does, but in a mathematical way. As time passes, this vector changes, showing the particle's movement. It's a powerful tool that allows us to track motion with incredible precision. By understanding position vectors, we can describe complex motions using simple mathematical language, turning seemingly complicated movements into clear, trackable paths. Velocity is more than just speed. It's speed with direction. In rectangular coordinates, we break velocity into its x and y components. This means we can understand not just how fast something is moving, but exactly where it's going. Picture an arrow that shows both the speed and direction of motion. By analyzing these components, we can predict an object's path, understand its changing direction, and even calculate future positions. It's like having a dynamic roadmap that constantly updates the object's journey through space. Acceleration is the rate of change of velocity. Think of it as the change in motion itself. In rectangular coordinates, we again break it into x and y components, showing how speed and direction are changing in each dimension. It's like having a sophisticated GPS that not only shows where you are, but also how quickly you're changing speed and direction. Engineers and physicists use these acceleration components to design everything from roller coasters to spacecraft trajectories. Understanding acceleration means understanding the dynamic nature of motion itself. Rectangular coordinates are essential in various engineering applications, particularly in analyzing projectile motion and planar movements. In projectile motion, functions xt and yt describe the horizontal and vertical positions of a projectile, helping predict its path. For planar motions, such as vehicles moving along straight or slightly curved paths, rectangular coordinates provide a simple and effective way to analyze the system's movement and ensure accuracy in design and operation. Let's delve into the concept of normal and tangential coordinates, which are used to analyze curved or circular motion. In this coordinate system, the tangential direction is along the trajectory or path of the particle. The normal direction is perpendicular to the path and directed toward the center of curvature. The particle's position is described by its path, represented as a scalar value, which measures the arc length along the curve. The velocity vector is always tangential to the curve and is expressed as vector v equals v times t cap, where v is the speed, defined as the rate of change of the path length with respect to time. Let's explore the components of total acceleration in normal and tangential coordinates. Tangential acceleration. This represents how quickly the speed of a particle changes along its path. Simply put, it's the rate at which the particle speeds up or slows down as it moves. Normal, centripetal, acceleration. This indicates how quickly the direction of the particle's velocity changes. It points toward the center of the curved path the particle follows. To express it in simpler terms, it's the force that keeps the particle moving along a curved path instead of going off in a straight line. Together, these components help us understand the particle's movement along curved paths, giving us a complete picture of its motion. These components can be expressed together in the equation of the total acceleration vector, showing how both contribute to the overall motion of the particle. The magnitude of the total acceleration is the square root of the sum of the squares of the tangential and normal accelerations, representing the combined effect of these two components on the particle's acceleration. Let's dive into the concept of the radius of curvature. This quantity measures how sharply a curve bends at a particular point. Mathematically, it's expressed as the absolute value of the numerator and denominator of a fraction. The numerator is the expression 1 plus dy divided by dx squared to the power of 3/2. The denominator is the expression d squared y divided by dx squared. In simpler terms, if you have a curve described by a function y equals f of x, the radius of curvature tells you how tight the curve is at any given point. It's a critical concept in fields like road design and roller coaster engineering, where smooth and safe curves are essential. When comparing rectangular coordinates and normal tangential coordinates, we consider several aspects. In rectangular coordinates, we use fixed x and y-axes to describe motion, which is suitable for straight or planar motion. The acceleration components are along the x and y-axes, which are denoted as a sub x and a sub y. This system is generally used for analyzing general 2D motion. On the other hand, in normal tangential coordinates, the reference directions are tangential and normal to the path of motion, making them ideal for curved paths or circular motion. The acceleration components here are tangential and normal, represented as a sub-tej and a sub-n. These coordinates are particularly useful for studying circular motion and the dynamics of vehicle turning. Understanding the distinctions between these coordinate systems allows us to choose the appropriate one for analyzing different types of motion, enhancing our ability to solve engineering problems efficiently. Rectangular coordinates are crucial in analyzing projectile motion and robotic systems, enabling precise movements and positioning. Normal and tangential coordinates are vital for understanding vehicle dynamics and circular motion, ensuring stability and performance in applications like race tracks and satellite orbits. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.